So we were talking about qubits, and the two examples are going to be photons, the polarization, and spin 1/2 particles. So we were talking about photons and electromagnetic waves. And the last thing we left off with was this idea of a Jones vector. Right? We argued that an arbitrary polarization of an electromagnetic wave can be described by a two-dimensional complex vector called the Jones vector, and it has this general form. Where these guys, the X and Y, are just the linear polarizations along the X and Y directions. So again, just to remind you, it's got the X and Y, you got the Z, the direction of the propagation of the wave. You got some electromagnetic wave. And this is the polarization vector. And it's generally described by this complex Jones vector, which includes a possible complex or imaginary, this includes this phase piece, which allows for circular polarization, where the polarization vector can rotate around. So this here I drew a linearly polarized wave, but in principle you can imagine a kind of helical wave propagating along where the polarization vector rotates. Okay, so how do you make this? How do you make any kind of Jones vector? You can do it with a kind of device. It's called a lambda mu polarizer. It's called that because often this is called lambda, and this whole number is called mu. And the way you do it is you send the wave through a phase shifter. This is a birefringent material. It means it lets light through in different ways depending on the polarization. So if it's typically a crystal and it has some kind of orientation inside of it, some crystalline material, and when the light goes through it, if it goes in at a certain polarization, it goes through in a different way relative to the perpendicular polarization. You can put in another phase shift, a birefringent material here, and in the middle you put a polarizer. And the polarizer it lets light through as long as it's polarized along a particular axis here, theta. So what happens in here? So light comes in, and then one of the polarizations, like say the light that's polarized in and out of the plane, it goes through one path. The birefringent material splits up the polarizations. And then the other polarization, let's say up, down in the plane, goes this way. And then both of these pass through the linear polarizer. And then what happens is here you put a birefringent material in the opposite orientation so that it shifts the polarizations back together. And so in the end, the light wave comes out. And so we can ask what happens, in general to the to this light wave. And there's 3 steps. So let's look at it one step at a time. In step 1, your initial Jones vector, let's say there's some, arbitrary polarization. This goes to, after step 1, it gets shifted. Let's say the Y polarization gets shifted by a phase factor. So you go to a new 5 prime, and nothing happens to the, actually, to make it consistent with this picture over here, let me flip these around. Any questions so far, though? We're just making a device that can generate an arbitrary polarization. That's what we're trying to show. Let me call this one the Y direction, the one that gets shifted. And then the X direction is in and out of the plane. So that's the one that doesn't change. So the X doesn't change, but the Y, it develops an e to the minus I eta. So we can just have a birefringent material that adds a relative phase to the Y polarization piece. Okay, so in step 2, you take your 5 prime and you just project it onto that polarization direction. And it's the same as we learned about projection operators. You just take the polarization corresponding to the, the linear polarizer direction, and you dot it into your incoming Jones vector. And that just gives us the linear polarization of the theta direction. It's theta multiplied by the inner product, which is EX cosine theta. That's the component along X, plus EY sine theta, eta minus eta, like that. So that's what you get after step 2. And now we can go to step 3. Step 3, it's the reverse of.
I did have a question again. Could you? Because
yeah.
I was walking in from my car, and what was the nabla symbol? What was that representing? Nabla there. Is that nabla, or is that just some fancy E, or what is that? The sine E to the I nabla.
Nabla, isn't that this?
No, I mean, what is that symbol that's over there? E to the I what?
Eta.
Eta. That's what I meant to say. Yeah, eta. Yeah. What is that? What is the value for that? What does the eta represent?
It's the phase shift of the birefringent material. So a birefringent material introduces a phase shift between the polarizations, and it's kind of drawn here. It's this difference in the paths. It takes the Y polarization and shifts it by this phase factor.
Right. Okay, so it's the phase shift. Okay. All right, thank you.
Birefringent. Okay, so in step 3, you just do the reverse. You get a phi triple prime now. That's after step 3. And what do you get? Well, along the X direction, you just get the same amplitude multiplied by cosine theta, because that's so theta is, what's theta? Just to make sure we have it right. It's just the combination of the X and Y. It's the linear polarization along the theta direction, right? Because there's no complex phase. Okay, so what do you get? So after the phase shift, the X component doesn't change. So you just get EX cosine squared theta plus EY sine theta cosine theta e to the minus I eta. That's multiplied by X. And then for the Y component, you get, a shift, which is e to the x, and now it's the opposite shift, so you get an I eta, a plus I eta. And then you're projecting on to the y direction, so there's a sine instead of a cosine, so you get a cosine theta, sine theta. And then you get an e to the y sine squared theta, y. And the two exponentials cancel, right? The phase shift in the y piece cancels out because e to the minus I eta, and then you multiply by e to the plus I eta. Okay, and now you can do some algebra and rewrite this. We can rewrite this in terms of these lambdas and mu's. This becomes, let's see, EX lambda squared, that's just the cosine squared, plus EY mu star, right? That's sine theta times e to the minus I eta. That's mu star. And then we have a lambda from the cosine. And all of that is multiplying x. And then over here we have EX. And then this piece must be mu. This piece is lambda. And then we have e to the y, and then this piece, the sine squared, must be just the magnitude of mu squared, right? And so we can rewrite this in an even nicer way as your arbitrary polarization multiplied by so does that work? Let's see. Yes, so we can factor out a lambda from here, from the x, and from here we factor out a mu. And so this is what we get. We get some complex number times lambda x plus mu y. This is arbitrary polarization, right? That's what we wanted to show, that we can generate something that it gives you an arbitrary polarization. And so with this one device, you can construct any kind of polarization you want, a linear polarization, a circular polarization, whatever you want, a general vector of this form here, psi. And moreover, we can write this as a projection onto one of these arbitrary Jones vectors, because that's what this is. It's a projection onto one of these psi's, starting with phi. And this projection is the device. It's what the device does. Projects onto the phi state. And we can write this device projector in matrix form if we want. It's just lambda squared, lambda mu star, lambda mu, and mu squared. Yeah, so that's how you would do it. And what else? We also didn't mention this last time, but the intensity is, of course, going to be proportional to, so say you're coming in with, let's see, coming in with some initial vector E like that, and then in the end, you come out with a vector E prime. Then E prime is just going to be this P psi projector acting on E. And if we restore back the overall amplitude of the electric field, we would get that it's E0, some overall amplitude. Then we get this psi psi acting on our initial vector, which is phi. So this is just E naught times the initial Jones vector. So then the intensity would just be the magnitude of this thing, the inner product with itself. So you get E naught squared, and then this becomes the magnitude squared of phi and psi. So that's how you get the intensity of the light. Or for a photon, the probability of detecting the photon as it comes out. Okay, does that sort of make sense so far? And, you know, as an aside, if you know, phi is equal to psi, if you start with the same polarization as that you're trying to generate, then of course this gives you just one. So all of the light gets transmitted through, and you know, so then the intensity is just equal to the initial electric field magnitude squared. And we usually just drop the electric field portion and just think about everything being normalized by the electric field amplitude for E and M waves. But for a photon, these are just become probabilities of detection. And so in that case, you know, you really would just set E naught equal to 1. Okay, really, any questions? There's also a special perpendicular initial vector you could try, which is, you could call it like psi perpendicular. And what it is it's minus mu star x plus lambda star y. And what you can show is if you take psi and you dot it into psi perp, or you take this projection, you just get 0, because this inner product gives you 0. So this is kind of a vector perpendicular to psi, which is, you know, oops, the Jones vector we're trying to generate. So again, you have this Jones vector, and if you initially start your phi in a direction perpendicular to that direction, then of course nothing comes out of this lambda mu polarizer. You just get 0. So in a sense then, psi, which, let me write them out again. Psi, which, let's see, is lambda x plus mu y, and this perpendicular vector these form a new basis for polarization. And we can, of course, go from the xy basis to psi perp using the following matrix, right? You take xy to get psi, you get lambda plus mu, and for the other one, you get minus mu star lambda star. And what must be true about this matrix? Anyone?
Does it have to be Hermitian?
Not quite.
Unitary?
Yes, it must be unitary. Why is that?
Because it has to preserve the norm of the space.
Hello.
That's right. Sorry. Yeah, that was right. It preserves the norm. It transforms from one basis to another. And so if you have a transformation like that, it has to preserve the orthonormality of the basis. You have to maintain that this is, 0 and that x dotted into itself is 1. Same thing for psi and psi perp. Okay, any questions?
You said maintain orthonormality when you're transforming from one basis to another. Is that right?
Yes.
Okay, just making sure. Thank you.
So this is a unitary. And you can check for yourself that it's unitary.
Yeah.
Okay, so that's how you make an arbitrary Jones vector, or an arbitrary polarization of a photon. And so let me just mention something weird about photons. So this all makes sense for E and M waves because we're used to adding together electric fields and using superposition and so on. It makes sense. But for a photon, it's a little weird. It's a little weird that the Jones vector describes the state of a photon. And you can really see that by considering the following kind of experiment. Say you shoot a photon and you pass it through 2 polarizers, right? One at angle theta and the other at some other angle alpha. And you ask, as it goes through here, what's the probability that it comes out? And we know that, the probability is going to be proportional to the intensity of the electromagnetic radiation that, corresponds to that photon, a gamma for a photon. And so we can kind of figure out what that is, right? The electric field here is going to be, it's going to look something like, cosine theta x plus sine theta Y. And then when it passes through this polarizer, the whole thing is going to be proportional to these components dotted into this new direction alpha. This is awkward notation. This is proportional to, and this is the letter alpha. Okay, but this is just a quick little calculation. So you'll get something proportional to, well, you'll have the linear polarization along alpha, but the whole thing is proportional to the dot product, right, between these two directions. And that's cosine theta cosine alpha plus sine theta sine alpha. And so the intensity, or the probability, let me put probability. The probability is just cosine theta cosine alpha plus sine theta sine alpha, that whole thing squared. And then of course you have the alpha, but this is just one, the linear polarization vector piece.
What is the probability of here?
This is a probability of sending in a photon that it comes out.
Polarized by alpha.
Sorry?
But I know that it's probability that it comes out, but is it probability that it comes out polarized a certain way?
Yes, polarized along alpha, yeah.
Right, okay.
That's how these linear polarizers work. Typically, what is a linear polarizer? It's a piece of material that has long molecules in it. So it looks something like that. And then when light comes in, the electrons in this material, they only like to oscillate along the direction of like the long molecules, typically some polymer or something. It's like a piece of plastic. Have you ever seen like polarizing sunglasses or something? You know, it's plastic. So the electrons oscillate along just one direction, so it only lets light pass through as long as it's oscillating along that direction. So that's how they work. So
but
you have,
usually when they're describing polarization, they just use one polarizer, right? The light goes in, you put in a polarizer, you get a polarization. What is the purpose of using, like, you're polarizing it twice, it looks like, right?
yeah, this
Along
is just
there,
a
and then
thought experiment. I don't know if you ever had sunglasses with polarizing filters. If you take the two lenses and you stack them on top of each other, if you rotate one around, you'll find that if you cross the polarization directions, then no light comes through, right? It
right,
gets dark.
naturally.
What?
Okay, yeah, I get that.
Yeah, so we're just doing that, you know, the thought experiment. And I just want to illustrate something interesting about that. I haven't told you why I'm doing this, but that's what this is. It's just crossing two polarizers. Yeah. And the intensity of the light is the same as it's proportional to the probability that a single photon makes it through.
That makes sense.
If the polarizing directions are completely perpendicular, then no photons come through because a photon can't oscillate in one direction and then a perpendicular direction. Just, it's going to get absorbed by the material, right?
Yeah.
That's all we're doing. We're just trying to figure out their probability. And the probability is just the dot product between the two directions, the theta direction and the alpha direction. And I can rewrite this as cosine squared theta minus alpha. It's just a trig identity. So you see, if they're oriented in the same direction, if theta is equal to alpha, then, you know, the photon goes through with 100% probability. If theta and alpha are perpendicular, then this gives you 0. And this is called Malthus's law or something.
Yeah, it's Mellis law.
Mellis
Mellis law. Yeah, Malus law.
Malice?
That's yeah. That's that cosine squared theta law.
Okay, I don't know how to spell it,
Malus.
but that's
Malus.
um, it's Malthus, M law. Okay, yeah, I'll figure
Yeah.
out how to spell it for for next time.
Yeah, it's Malus.
Malus. Okay, yeah.
Yeah. That's a famous law with the cosine squared theta. We do it in so
Well, sure. Well, there you go. That's so you should know this piece.
I
But
know
if
that
you think
piece.
about it, what?
I said I understood that piece, but I took the quiz and I should have waited until after you talked about the Joneses stuff. Anyhow.
Um, oh, but there's no. Well, okay, there might be one. Um, all right, so, but now, if you really think about this, it's actually quite weird because if we go back to these phase shifters, we could in principle put them in here between the two polarizers. And we could split up the light. We could split up the photon so that if it's polarized one way, it goes through this upper path, and if it's polarized the other way, it goes through this lower path. And then you would have expected that if you can keep track of which path the photon went through, remember here the photon is polarized this way, here it's polarized that way, then you should be able to just keep track. Either the photon goes along this path or goes along the bottom path. And so then the probability of coming through as it travels along, well, the probability that it goes in the upper path would be proportional to sine squared theta, because that's the y component of the polarization in the theta direction. And if it went along this upper direction and it came back down and hit this alpha, then in order for it to sneak through, there would be an additional probability of sine squared alpha, because now you're coming up here with this y polarization, and you'll only sneak through this alpha with a probability sine squared alpha. So this is kind of the upper path probability analysis. And then you would think that a mutually exclusive option is that a photon comes out of here and goes along the bottom path where it has the polarization in the x direction. And there, the chance that you come out of here with an x polarization to begin with must be cosine squared theta. And then if you go along this bottom path, you keep going and you hit the second polarizer with an x polarization, then the probability that you sneak out must be cosine squared alpha. And so this is for the lower path. And that's not Mallus's law, and not what happens. And they're very different. This is sort of like a classical version, and this is the true result, the thing that actually happens. And there's a lot of interesting aspects to this. You can, for instance, what if you choose alpha is equal to pi over 4? Then from here, you'll get that this is just equal to a half. because the sine squared theta and cosine squared theta will add together, because sine squared alpha and cosine squared alpha are both going to be equal to 1 over,
Well, 45 degrees is square root of 2 over 2.
That's right. Square root of 2 over 2.
2 over 2, yeah, for 45.
Yeah, so you'll get, all right, I'll just do it. So it's a sine squared theta square root of 2 over 2, or 1 over 2, or square root of 2 squared is 1/2.
Yep.
So you'll just get this. It'll be independent of theta. But here, what do we get? Alpha is equal to pi over 4 gets you, well, nothing. It just gets you cosine squared theta minus pi over 4. And so this is very different, right? This is completely different from 1/2, depending on the angle theta that you come in at. And so you can get, you just get completely different behavior when thinking about the photon as a particle that can travel through these two different paths, versus what actually happens is that the photon travels along both of these paths. The two paths interfere with each other. And if you don't keep track which path the photon actually went through, then the two paths will interfere and you'll get, this result, even when you put in those two birefringent materials. Because the photon behaves like the electromagnetic wave would be expected to behave. Any questions about that?
Yeah, so are we not missing, now I understand that, like I said, it behaves both like a particle and a wave. That's what you're saying, which is weird, because it doesn't behave like you said. If it's not as a particle, it doesn't add up the same as a wave, right? Because it goes in both places. But what we're missing here, though, is that it's being observed somehow by some system, and doesn't that affect its probability or its outcome, right?
Yeah, so if you actually stuck in a little detector here,
Yeah,
and like observed somehow which of these paths the photon is going in, then you would get this result, actually. And you would ruin the Mallis's law. So yeah, that's true.
so that would be one way around, I would think. So then the other way is okay, as long as there's an observation, then we'll get that, even though really without observation it behaves like Mallis's law. That's why it's a law.
That's right. Yeah, that's right. And that's the weirdness of it. And I guess photons are kind of opposite of electrons from the point of view of intuition, because we're kind of used to thinking about things like Mallis's law, because we study electrodynamics, where superposition of waves is a very sort of intuitive thing. But for photons, we have to recognize that there are also particles, and in principle could be detected and their location could be resolved. And so then that sets up, the usual kind of wave-particle duality that exists in quantum mechanics.
See, that's why I think thinking photons as particles, when I was told another way is that they're like perturbation of the field. They're like something caused by, I don't know, is it truly a particle per se? If it's a perturbation of something, is a photon, that's where it
a
gets
particle is an excitation of,
right?
The corresponding field. But it still has an extent. You can detect it at a particular location. You can detect an excitation. So it's still.
I guess, yeah, I can see that. Yeah, I don't know.
It's still quantized in that way. Okay, so there's a kind of fun. Before we move on to. Before we move on to spin 1/2, there's a fun kind of thought experiment related to this, which is called the Elitzer. I'll spell his name. What is it? T. It's the Elitzer-Weidman bomb test. Has anyone heard of this? Has anyone seen this?
Nope, not me.
I might have. I don't remember it.
Okay, so
That's
the
great.
idea is it's the same kind of deal as the phase shifters, except you use like a half silvered mirror to split up a photon into two pieces. It's a half silvered mirror. So basically all it does is it gives you a 50-50 chance of either letting this photon through or reflecting it. So this is a half silvered mirror. And so this is a kind of device. And here you would have a regular mirror. Maybe I'll put these in blue. So the photon can come in here, can get reflected and go on this upper path where it hits another half silvered mirror. Let me get rid of this. And at the half silvered mirror, it'll again either get reflected or get transmitted through. And you have two detectors set up, one here and one here. And here you would get another mirror. This is a kind of device you can make, and you can use it to test bombs. So I'll show you how. So okay, this is without a bomb in the kind of bare bones situation. You send a photon in here, it goes along. You know, if we think about it as a particle that's localized, it either goes along the bottom or the top path. And you'd think that, you know, there's a 50-50 chance of going in the bottom or the top. And then there's a sort of 50-50 chance of going to the top or, you know, to up or to the right to the two detectors. But of course, we know that if we just shine light through this, the electromagnetic wave at this point will interfere between the two different paths. And we can tune things just right such that the light never goes up. You just make the electromagnetic wave destructively interfere up here. And so the light in the bare bones case, the way we set up this device, it comes in here and it always just comes out here, right? The light just shines into this detector. So photon detector. Okay, so what do we do with the bomb? So we imagine a bomb with a kind of light sensitive fuse that can absorb a photon. And we put the fuse here and the bomb. We put it in the bottom path. And now if we think about it, there's two cases to consider. One is the bomb is a dud. And two is the bomb works. And we're trying to see if the bomb works or not, or if it's a dud. It's a bomb tester. We want to make sure that it's a working bomb. So in the case where it's a dud, we know that the light sensitive fuse doesn't work. So in case one, the photons are always just let me just call this D1 and D2. In case 1, the photons, you send photons in here one at a time, basically. And if it's a dud, then, you know, it's as if the bomb isn't there, right? The light-sensitive fuse doesn't work. The bomb is a dud, so the photon interferes between the upper and lower paths, and the photons are always detected at D2. Now suppose the bomb works. Then you imagine a photon coming through here, this half-silvered mirror. There will be a 50-50 chance of it either getting reflected or passing through. And if it passes through and hits the fuse, the bomb explodes. So in case 2, if it's a working bomb, then 50% of the time, the bomb explodes. Now, the other 50% of the time, the photon will go up here into this upper path, and then it'll hit this half-silvered mirror, and there'll be a 50-50 chance of it being detected at either D1 or D2. So if out of that 50% chance, there's half and half chance of being detected at the 2 places, then 25% of the time, it'll be at, it'll be a photon click at D2, and the other 25% of the time, it'll be a photon detection click at D1. And it is this event, if you shoot a photon through and it's detected at D1, that can only mean that the bomb is working, right? And that's really an amazing thing, because, you know, if you ever detect a photon at D1 and nothing exploded, like if something exploded, then the bomb obviously works. But if something didn't explode and you found a photon at D1, you automatically know that the bomb is working, even though you never exploded it.
Wait, but what about it? The light sensor not working though, even though, because that was a chance, remember? So we know
That's what I
that.
mean by a dud. A dud is one which the light sensitive fuse doesn't work.
Mhm.
Wait, what?
Yeah. So so if it's a dud, we wouldn't know if it was a dud or if it was working, because if it went that direction and it went up there and it got detected at D1, it could still be a dud or it could be
No,
working.
Yeah, that's what I don't understand.
it can't be a dud. Can't be a dud.
Okay.
If it's a dud, then it's not detected and they destructively interfere at the second red mirror.
I see.
Exactly.
So so if
Okay.
it's a dud, it gets destructive. I thought you were saying you can set it to destructive interference on that one. So it would just go to D2 no matter what.
A dud
The dud gets
doesn't detect, it can't detect the photon because it's a dud. So it
So it goes
must just
through.
be like as if the bomb isn't even there. So it just gives you the original setup, which is designed to have destructive interference
Okay.
at the second mirror.
So isn't
so
that how, like, the photon knows that the path is blocked when it's separated at the first mirror, though?
Well, that's just the thing. This whole thing illustrates the faulty nature of classical intuition about these things. It's just the photon doesn't, it's neither in the upper nor in the lower path. It's
both.
reality just isn't like that.
Isn't it both? Doesn't it go in both directions?
I don't know if I want to say it's both.
'Cause I think I remember in my quantum one that we had a similar thing, but it was with a black box, and we wanted to know if A or B was in that black box.
Right, I'm pretty sure you can make similar experiments, like with the paths with like electrons and neutrons as well. Like, this isn't specific to the photon, right?
No,
Yeah.
it's not. That's right.
Anyway,
But it just, Goes to show you the weirdness associated with the fact that a photon is described by this Jones vector. Is the same kind of mathematical object as we use to describe electromagnetic radiation. And for electromagnetic radiation, it's very natural for us to think about superpositions. We add together vectors just as we do in the Hilbert space.
Okay,
And it's that superposition that leads to these very weird effects. Yeah.
so if it's a dud, you
Yeah.
get destructive interference, right?
Yeah.
And you detect it only at D2.
Yes.
But that's saying that when you shine the light in the first half silvered mirror, that you have a part of the light going up and a part of the light going sideways, perpendicular. Is that what that means? How would you get destructive interference otherwise?
Well,
Does that make sense? I'm just trying to follow.
it makes sense, but you can think about, yeah, you can, fine, we can think about it in the classical electromagnetic radiation sense. Yeah, you shine a bunch of photons through, and half of them will go up and half of them will go through, and then they'll construct to, they'll interfere at the second near.
Okay.
And the weird thing is that a single photon also does that.
Yeah, that's what I was trying to follow. Okay.
That's why it's weird. Yeah, is that a single photon behaves as if it were many, many photons, at least in terms of the constructive and destructive interference. It's like it interferes with itself.
It's like the Young's double slit almost, right?
It's exactly the same. Yeah, it's the same weirdness. That's right.
Okay, cool. I follow. Thank you.
Yeah. Any more questions? You can actually fancy this up and get to an arbitrary efficiency. So this is not a very good detector because, like half the time the bomb explodes if it's a working bomb, so that's not very good. But you can actually make fancier versions of this where you put the fuse in like an optical cavity, and you can get like efficiencies of 99%, where like only 1% of the time the bomb explodes. There's like fancier versions of this, but this is the simplest.
Wait, so this is a real thing? This is just a thought?
No, yeah, this was tested. Yeah, this is a real thing.
Okay. All right.
Yeah.
Neat.
What else?
So that begs the difference is there a single photon, or can we see, or is a photon many photons, or is there only just one photon if you think about it? Since it behaves like many photons even though it's a single photon.
Well, no, I mean, this works with a single photon, and how you know it's a single one is you detect a single click in the detector. So you can check this bomb one photon at a time. Like photon detectors, they detect clicks, so that's how we know, photons are particles, is that if you shine some light, you could detect the particulate nature of it when it hits the detector.
Yeah. Weird.
Yeah, it's weird. Okay, so that's the photon. There's something else I wanted to say about this. Yeah, so I'm going to clear this. Just a little bit about more basis vectors for polarization. And we, of course, have the X and Y basis, which we started with. And we can think about projecting onto that, which is just, this, or in matrix form, it's 1, 0, 0, 0 in the X and Y basis. But we can also, and we also saw that we could use an arbitrary basis in terms of an arbitrary Jones vector and the Jones vector perpendicular to it. In particular, as a special example of that, you can also look at the right and left circularly polarization vectors. Those are also a basis. And you can write their projection operators as follows. This, when you act on, the X and Y, it'll spit out the left and right polarizations. This is R, and L, L. There's an interesting operator to consider, which is the difference between these two projectors. It's the last thing I'll say about photons. You can show, it's pretty easy to show that if you act with this operator on R, you'll of course get back out R. And if you act with this operator on L, you get back out minus L. So this is the right and left circularly polarized light is an eigenstate of this operator. And moreover, this thing is Hermitian, because these things are Hermitian. Right, it's just R minus L. And another interesting thing about this is if you exponentiate this operator and you take e minus I theta sigma z, you can show that this is equal to cosine theta minus sine theta cosine theta. So it's a rotation matrix. And what is this thing? We know, so this is a Hermitian operator, right? And so we expect it to correspond to some measurement. And does anyone know what measurement it could possibly correspond to?
I mean, wouldn't that be the direction of the polarization? I mean, if it's a rotational thing, is that what it would be? I mean, because that's just the rotational matrix, right?
Yeah, this is
At your left, so that would
version of
say,
it. But this itself, what physical quantity might it be associated with, related to the photon?
mass, energy? Mass, no. I'm not sure.
Any takers?
What are the physical quantities of a photon?
What do you mean?
Yeah, what are the physical quantities?
Yeah. That has no mass, so.
Energy,
It's got no mass.
Energy wave, maybe energy, I mean.
Wavelength?
Yeah.
Or frequency and
Not,
wavelength, kind of.
Sorry?
Well, energy, frequency, wavelength, speed is constant.
Yeah.
Phase?
Yeah, there's one more that's associated with polarization.
Phase? I mean,
Pointing vector?
huh?
The
Pointing vector, yeah, that's the energy.
Well, a rotation usually gives you some phase, how does that phase relate to a physical quantity of a photon?
The
It's
spin.
definitely related to rotation. Yeah.
Spin, but that's the electron, not.
Yep, spin. Photon has a spin too.
Photon still has spin, it's just a spin of one.
It's angular momentum, right? If you have a photon traveling along the z-axis and its polarization vector is rotating around, that has an associated angular momentum along
Wait,
the z direction.
Sigma Z, that's one of the Pauli spin matrices, isn't it?
Yeah.
It'll be related to that. We'll see. But for a photon, it's got a spin, which is h bar. It's angular momentum. Remember on the homework, h bar, always angular momentum. So angular momentum times sigma z. This is the angular momentum of a photon.
Nice.
That's what you measure. And if it's right circularly polarized, you'll measure angular momentum of h bar. And if it's left, then you'll measure minus h bar, right? According to the right-hand rule.
Yeah. That's neat.
Yeah, so anytime you see an operator that's Hermitian and you know that, well, actually, it's whenever you find one, it's probably going to correspond to some physical quantity that you can measure. And you can get some hint of what it is if you know the eigenvectors. And here we see that it's the right and left circularly polarized light. And so we know that right and left circularly polarized light is one where, the polarization vector is rotating in a circle. So, something to do with rotation. And unsurprisingly, I guess that's the angular momentum. That's the physical quantity associated with this Hermitian operator. Okay, so let me clear this. So spin 1/2 is very similar in terms of the mathematics, but of course the physics is very different. So if you just remember what spin is, we're thinking about, again, angular momentum. So that's a little, the last thing was a good segue. So you have something rotating around at some r vector, and it's got some momentum. It's performing some orbit, and the area swept out by this r vector as it sort of goes along in this orbit satisfies this equation. A is sort of the change. This is the area. The direction of it is just according to the right-hand rule, so it's sort of up. This is the direction of A hat. This is equal to 1/2m r cross p. If you do right-hand rule, you see that the r cross p points up. And this is defined as 1/2m times the j vector, which is the angular momentum. If we integrate over a whole period of motion, if we integrate this equation, then what you'll find is if j is a constant, it's some constant vector, then you'll find the period over 2m just times j. So that's the area of the whole orbit. That's how we connect the two things.
Could you just say what A vector is again? I'm
It's defined as the magnitude is just the area swept out by the orbit as it's orbiting around, and the direction is given by the right-hand rule between the location of the thing that's orbiting around. You can imagine some particle orbiting around this circle, and it's the direction is given by the cross product between the position and the velocity, so r cross p. So we can imagine this particle orbiting around. If it has a charge q, then you'll get a current associated. You'll get a current due to this charged particle orbiting around. And you'll get a loop of current. And from there, you'll get, of course, a magnetic moment if it's a charged particle. And the units of that, or the relationship between A and mu is just, it's the current times the A vector, the area. And I is just Q divided by T, right? It's the amount of charge that goes around in a period T. And we can write this as Q over 2mj, just combining these two things. And this is often written as gamma j. So if basically we're saying if there's a charged particle with an associated angular momentum to some maybe orbital motion, then there will be an associated magnetic moment, which is proportional to the angular momentum. And the constant of proportionality, gamma, is called the gyromagnetic ratio. Hopefully you've seen this at some point, somewhere. And the weird thing about spin 1/2 particles is that they have intrinsic angular momentum. So in quantum mechanics, and it's hard to prove this in general, but maybe we'll talk about it later, particles have intrinsic angular momentum. They just come with it, like attached to it. So if you think about like a electron, it just comes along with some J. And of course, that means since it's got a charge and all, that, you know, this thing will come along also with an associated magnetic moment. And that's often how you detect the intrinsic spin, is you try to apply a magnetic field, and that'll couple to the magnetic moment that's induced by this intrinsic angular momentum. And spin 1/2 is particles that have intrinsic angular momentum given by h bar over 2. And then of course you can ask, what about the gyromagnetic ratio? Well, that's the hard part. This is like where the difficult physics comes in. It's not hard to get h bar over 2, but to get the magnetic moment, you need to know the gyromagnetic ratio, and that's the hard part. So this is the difficult physics associated with the magnetic moment. So like the gyromagnetic ratio for an electron is, as it turns out, -2. And it's hard to even get this -2. You get a whole series of corrections in powers of the fine structure constant that we looked at in chapter 1. And this is getting these kinds of corrections is the subject of quantum electrodynamics. And the whole thing is, of course, is proportional to the charge of the electron over 2m. So there's other corrections. This is a sort of a classical analysis of, an orbital motion. But if you dig deeper, the relationship between the magnetic moment and the angular momentum is more complicated. It includes effects from special relativity, for instance. And, it's not so easy. I can explain the minus sign. The minus sign just comes from the fact that electron is negative charge. But you can spend a lot of time talking about where the different numbers come from. This thing is called the G factor, but it's not really so important for us. The basic idea that'll be important for our qubit analysis is just that there's a magnetic moment that's proportional to the intrinsic angular momentum, and in quantum mechanics we'll just take for granted that particles come with their own little j, just come for free. And for spin 1/2, the magnitude of that little j that they get is h bar over 2. Okay, any questions? This is not so important. It's worth it to think about, if a particle comes along with its own angular momentum, how would you measure it? And you would measure it by making use of the induced magnetic moment. But to understand that, you really need to know the constant of proportionality, this gyromagnetic ratio, which is where all the fun physics comes in. Oh, wow, I'm running out of time. So, yeah, next time we'll continue this. We'll finish up with spin 1/2, and we'll move on to chapter 7, which is we're going to go back to math and develop the last bit that we need, which is infinite dimensional Hilbert spaces. Yeah, so the next time we'll finish the spin 1/2 and start chapter 7. So we're skipping quite a few chapters, but we'll go back to them later. It's important. So what we're doing is, just as this last bit here, what we're doing is we established the mathematics of Hilbert spaces and operators. We're doing some examples of finite dimensional Hilbert spaces. And then just the last bit to complete, quantum mechanics is we need to know what happens when your observables have a continuous range of values, like a position or an energy of a free particle, because a free particle can have an arbitrary kinetic energy. We have to know how the Hilbert space adapts to continuous values of observables, because so far all we said is that observables correspond to eigenvalues of a Hermitian operator. But from our examples, how many eigenvalues do we get? We get like 2 or 3. Here in 2 dimensions, we just get 2. And we'll need to know how to generalize that to get a continuous range of possibilities for a measurement. That's the last bit of mathematical development. And after that, it's all just applying it.